All right, so this is lesson 5.3 on the fundamental theorem of calculus. Very important lesson today, maybe the most important in the entire course, as you're going to see kind of how everything connects. So way back when we first learned about derivatives, we're going to see how that all relates to the areas that we've been studying in the last couple of lessons. Okay, so we're going to do something a little bit weird in the first example, but it will help us kind of understand where this fundamental theorem is coming from. So what we're going to do, and this is just a random function here that I've drawn in red, f of t, we're going to see, we're going to plot another function that's related to this function f of t, okay? And I'm using t as the variable along the horizontal axis for a reason, because I'm going to use x for something else. We're going to define a new function, which is g of x, and that's defined right here. So g of x is going to be the area from 0 to x of this function f of t dt. So we're going to make a table of values to help us understand what this really means. Okay, so g of 0 would be, just following the definition, it's going to be the area from 0 to 0 of f of t dt, which is of course 0 because that would have 0 width. Okay, so essentially I'm taking these x values and I'm plugging them in here, right in this position. Okay, next we're going to do x equals 1. So we're going to do the area from 0 to 1 of f of t dt. Okay, so on the graph, what that would look like is this area right here. And that is a triangle. We know the formula for areas of triangle. It's base times height divided by 2, or half times base times height. So that would be 1 times 2 divided by 2. So the area of that would be 1. I'm just going to separate this here. So this is going to be 1. And I'm going to start to plot these points on the graph we have. We're going to plot the graph of g of x here. So we had 0, 0, and then 1, 1. Okay, let's keep going. Now we're doing the x equals 2, so we're going to put 2 in for that upper bound. So that's the area from 0 to 2. So I'm going to keep that area of 1 and then add in this extra rectangle here. That has an area of 2, and so my total area now is 1 plus 2, which is 3. I'm going to plot this on the graph, sorry. All right, next I'm going to go to 3. And we'll see on the graph that this would now include this triangle here. So now I'm going all the way from 0 to 3. And if you add up those two triangles in the rectangle, we get a total area of 4. So I'm going to plot this here on the graph. Okay, that's the maximum my area is going to be, because now as I move to higher x values, I'm going to start to get some negative areas introduced. That is going to make my total area go down. So let's do the area from 0 to 4. Right, when I go from 0 to 4, I'll have the original 4 plus this new blue rectangle I'm adding in, which has an area of negative 1. So then the total area, if you add all those together, will be back down to 3. I'll plot that on the graph. Okay. And then finally, the last part, from 0 to 5, we'll have all of those added together, we'll have 2. And so end up here. Okay, we're going to draw a nice smooth curve through all of those points. So this is the graph of g of x on the right here. Now what I want you to notice is that if I compare the graph of f and the graph of g, the graph of f looks a little bit like the derivative of g. Let me show you what I mean. So if I was gonna, so this can go in your observations here. G of x, or sorry, I'll say it the other way around. It's a little bit better. F looks like of g, right? So notice, for example, like right here at x equals 3, the slope is 0, right? well, go ahead and look at the f graph. Yeah, see how it has a point at 0 there? Now look here at like this region here between 1 and 2, right? See that slope, rise over run, 2 over 1, right? The slope there is 2. Well, what do we notice over here, right? The slope, the y values are all 2. So in fact, this is true. The function f is the derivative of the g graph, but then the g was the integral of the f graph. So what we're actually noticing here is this kind of like inverse relationship between the derivative and the integral. Okay, so g is the integral of f, but then f is the derivative of g. Okay, so actually this is true, and that is the fundamental theorem of calculus. When integrals and derivatives are essentially opposite operations, it's like analogous to like when you say that square roots and squaring are opposite operations, or like adding and subtracting are opposite operations. Integrals and derivatives are opposite operations. Okay, so let's look at the official theorem here. So here it's just defining that same function idea again that we did above. So it says if f is continuous on the interval a, b, and g of x is defined by this same thing here, except notice they've made it even more general and just said it can be from any constant here. So if g is the integral of f from any constant a to x, then actually g, the derivative of g is f. So another way of writing this, and I think this kind of makes more sense, is if you write, if you take g, which is this, and you take the derivative of this. Okay, so you're taking the derivative of the integral. Essentially, again, those two operations, integration and derivatives, cancel out in a way. And what you'll end up with, right, just like if you squared a square root, you cancel it out. So then you're just left with this function here. But because we're taking the derivative with respect to x, it would be f of x. So these get kind of canceled away. So very cool, right? And then we'll learn actually how we can use this idea of opposite operations to in fact calculate integrals in the next part. But just a little geometric explanation here for those of you who like to really understand why this is true. When we're talking about the area under a curve, and then we're wanting to ask how that area is changing with respect to x, if we're wanting to take the derivative of that area, if you want to change it slightly, or the rate at which it's changing, go back to imagining these very thin rectangles, right? Infinitely thin rectangles. Well, the area would be changing at a rate that would be equivalent to whatever the height of that function is, right? The height of one of those rectangles. Well, what is the height of any rectangle? It's just simply f of x, right? So the derivative of the area is the function value. So that's your geometric explanation there of why that is true. Okay, let's just see it in action here. So if you have this function defined by the integral from 0 to x of 1 plus t squared dt, then determine the derivative of g. So another way to write that in different notation is find the derivative d by dx of this integral. Now, because we're taking the derivative with respect to x, derivatives and integrals we've just learned are kind of opposite operations. They essentially cancel each other out. And so we just have the original function. But because we're taking the derivative with respect to x, the variable in the function changes. Okay. But essentially, you'll just get that same function back. Okay, very cool. Okay, on to part 2. Part 2 is much more useful. If you do some, and you can prove this, but I'm going to skip the proof today. If you want to see the proof, I'm sure you can Google some videos for it. But essentially part 2 sort of is derived from working with part 1. And if you actually have an integral to calculate, because you want to do the opposite of the derivative, essentially you take the antiderivative of whatever the function is. Okay, so you take the antiderivative Okay, so the opposite of the derivative, and that's why we learned antiderivatives in the previous chapter. It was kind of a preview to this. And you evaluate it at the two bounds of your integral and you subtract. And that's going to get you the actual numerical value of the area underneath the curve for any function, okay? As long as you can actually find the antiderivative. Now, sometimes it's impossible to find the antiderivative or very difficult, and so that's where it becomes challenging. But if you know what the antiderivative is, then you can actually calculate the area under the curve, okay? So let's do some simple examples, and then we're going to get into more complicated examples in the next lesson. But just to start here, okay, so I'm just going to draw a picture here for this one too. Okay, so we've got this function x squared, just because you should be able to, like, you really need to understand what you're doing when you're evaluating these. We want to find the area between 1 and 3. So what that looks like, right, x squared actually looks like this. I should draw it properly, right? I want to find this area that I'm shading in blue here. Right, so what we've just learned is that integrals and derivatives are opposites. So to evaluate an integral, what I want to do is find the antiderivative, the opposite of the derivative. Okay, so remember your antiderivative rules. What you do is you do the opposite of the power rule for any power. You bump the power up by 1, and then you divide by the power. And what we end up doing is we subtract this answer evaluated at 3 and 1. So there's a neat little way to write this. We write this bar notation. So if you haven't seen this before, this is what it means. And we write 3 and 1 here. And what that means is we're going to evaluate it at 3 and at 1 and then subtract those numbers. So we're going to evaluate this at 3 and we're going to evaluate this at 1 and we're going to subtract. And you can use a calculator if that's allowed, or you can just do this in your head. But you don't want to round your answers. You want to give an exact number. So please leave your answers in fraction form, okay? Or if there's a irrational square root involved or something like that, you want to just leave it like that. So that evaluates to 26 over 3. So just leave it like that. Okay, so that's the exact area of this blue region, right? Okay, let's do the next one, e to the x. So we know that the antiderivative of e to the x is just, again, e to the x. And we're going to evaluate from 4 to 0. So we're going to plug in 4, we're going to plug in 0 and subtract. Now this we will get an irrational number, so you should just leave it like that. E to the 0 you can evaluate, right? This would be the final answer. But if you want to know numerically approximately what that is, feel free to plug it in. And you'll get about 53.6. Okay, so the area of e to the x between 0 and 4 is about 53.6, but it's exactly e to the power 4 minus 1. Okay, let's do a cosine one. Okay, so kind of a different, like 4 different examples, 4 different types of functions here. But again, all pretty simple with simple antiderivative rules. We'll do some more complicated ones in the next lesson if you're interested in those. Okay, next one, cos x. So the antiderivative of cosine of x is sine x. And again, we're evaluating at pi and at 0. Sine of pi, of course, is 0. Sine of 0 is also 0, so the area is 0. And you might ask, oh, how can that be? How can the area under a curve be 0? And that's because of symmetry. So I'm going to draw this function sine x. Right, looks like this. And here is pi, right here. Oh. 2 pi. So when I'm going from 0 to pi, oh, sorry, I just drew sine x. I meant to draw cosine of x. I was like, wait a second, the area is not 0. See, this is why it's good to check your answers. Cosine of x looks like this. There we go. I was very confused for a second there. Okay, back on track. From 0 to 2 pi, you actually see there's 2 different regions, one above the x-axis and one below And the reason it's 0 is because the positive and the negative cancel out, right? There's symmetry in that function. So that's why it's 0. It's not that it's just like a flat function with no height. Okay, last one, kind of an interesting one here. I like this one because we're turning an irrational number into something that's rational, which I find really cool. Okay, so I'm going to draw this one as well. So we're looking at the graph of 1 over x, which on the positive side looks kind of like this, right? And we're going to go from 1 to e. E, remember, is an irrational number. It's like pi. So I would expect, right, that this answer would be irrational, but in fact it is not, which I think is really cool. So we're going to do the antiderivative. Now 1 over x has a special antiderivative. It's ln x, because recall the derivative of ln x is 1 over x. The bump the power up by 1 trick doesn't work for 1 over x. Okay, and then we're evaluating at e and 1. And so I'm going to get ln of e minus ln of 1, which is just, and we know that ln of e is 1 and ln of 1 is 0. So I actually get 1, which is really cool. So this has an irrational width here for this region, but the area is exactly 1. I think that's really interesting. Anyways, okay, that's it for this lesson. So next lesson we'll learn how to do some more complicated integrals.